Hello, my name is Jean-Raphael Mercier for Team 3 for the Friday 7:30 a.m. lab. And this is for Lab 3 in EAS 3810C. And what we're doing here is showcasing the 10-degree angle of attack flat plate in the wind tunnel simulation. So a viscous flow over said flat plate, and we're going to be using the wind tunnel that we previously made in Lab 2, and then just inserting a blockage inside the wind tunnel in order to do our simulation. So first, I'm going to open up geometry in Fluid Flow and pull up the wind tunnel. I've already ported over the wind tunnel from the previous lab, and as we can see here, as everything pulls up, here's the wind tunnel. Did not mean to do that, but here's the wind tunnel with the blockage. And then right there is the test section of the wind tunnel itself. So as you can see, there we go. As you can see, here is the blockage itself. Now I based this off of the horizontal flat plate that was used in part 1 for this lab. So using the dimensions of the plate, I based it off of the dimensions of the test section, which is a 6 by 12 inches, and I converted that to centimeters. So using Lab Excel here, sheets, I knew that the test section was in inches. I converted it to meters, and then using this, I was able to get the dimensions of the flat plate. So whereas with the vertical, I had the vertical distance be 10%, and then for horizontal, I had the horizontal distance be 10% blockage. So for the 10-degree flat plate, all I did was consider changing the dimensions of the plate every 10 degrees. So I took the dimensions divided by 9 and then added that change onto the current, or sorry, subtracted that change to the current dimension to get the length of the plate itself at the time. So in this case, it covers this distance, which if I pull up Workbench once more, we can see right here that the length here is about 2.7 centimeters, or a little less than 10% of the distance, and the other part of the plate is I put about 100th of that, just so that there's little blockage here, and it's mainly focused on the blockage of the angled plate. So the dimensions are exactly the same for the wind tunnel on the previous lab. So after I place the blockage in, probably around the direct center, which you can find from just the hypotenuse of one edge of the wind tunnel to the other, and then it would cross over here. So that's where I started with the dimensions, and then gave it an angle of 10 degrees, which I can show by this. So from here to here, stretching that out, 10 degrees. So 10 degrees from here to here. Now, after making that wind tunnel, I went to Tools and Name Selections, and then I identified each part of the plate here as individual parts, as the bottom, top, tip, and tail. This will help later, and if you wanted to, you could see the different forces affecting a particular part of the plate, but otherwise we're going to be taking the average forces affecting the plate. I need another name selection. So I identified, scrolling back out, I identified here as the velocity inlet, here as the pressure outlet, and then the plate itself as well as everything else as the walls. So you would hit generate and it would fill everything in, leaving the plate itself blank. Once that is done, we can close out of that. Like I mentioned, I'm going to go to mesh. Should be pulling itself up. Segments parallel. So once it is pulled up, we should have be able to see the wind tunnel and start meshing it out. You can see it's starting meshing, so it's just taking a while to load. Okay, so after some time has passed, it's now ready. So now we can pull up the generator, and as you can see here, here's the model, the wind tunnel with the 10% blockage, and all of our name selections are here already. Our inlet, outlet, the flat plate itself, and the walls. For the generator, it is just like the previous lab, where under mesh, when that pulls up, under mesh, we use the triangle method. Pull this up. Yeah, we use the triangle method, and then we set our mesh to about 0.002 for the element size, and then we generate it, and then that brings up all of our lovely, lovely triangles here with the blockage inside the wind tunnel. Now, to save time for the purpose of the video, I didn't show the generation. That takes a long time. And as a note, I find it easier doing the named part of selection during the previous part in the workbench, so that here, again, it saves time. So it's already all written down. That part wasn't so bad. So like I said, just like in the previous lab, you just click method and then select the method that was needed. In this case, it was triangles, the area that needs to be generated. And then if you needed to, you'll just go to name selections and then just start clicking on the pieces and then name them itself. So that part is easy. It's just like the previous parts. So moving on, closing our generator. Now we can go to setup, which I'll talk through that since it's already done, but I can run it one more time to show for the purpose of the video. And the setup here is where we're going to be inputting our information and then getting our required data. So to do the required data, we would first need the velocity of the test section. So as you can see here, since this is all simulated, I didn't use the calculated, the measured values of the test section from the previous lab 2, where there was nothing in the flow and we just increased there was no blockage, we just increased the velocity through the wind tunnel. So using the formula from that lab, where it was just 0.2489 times the frequency that we're going in, minus 0.3718. That gave us the test velocity. And then using said test velocity and the area ratios, A test V test is equal to A in V in, I was able to calculate the velocity coming in to the wind tunnel. So pulling that up, it looks like it's ready, or it's just about. Ooh, I didn't even notice that was open. So, building, building, building. Takes a while to load. Almost done. Done. Excellent. Okay, so then here's our mesh for the wind tunnel. Inverted zooming in controls. As you can see, there is the blockage. So then what we would do, setting up, making sure our models are all working, our energy is set to on. So right click, there you go. We know we're in viscous. Make sure that, like the previous lab, it is set to K epsilon that we are measuring. Standard enhanced wall treatment for better measuring of values. Just click OK. You know that. Okay, everything else should pretty much be left alone. Discrete phases, nothing we really need to do there, so we're done with the model itself. Materials, this should already be set. Our fluid is air, and our solid is aluminum. This theoretical measurement. So nothing with solid zone definitions. Boundary conditions, we would go to our inlet. So you can see here, I renamed it the velocity inlet. We would double click. And here was we would put the velocity coming into the wind tunnel. In this case, from our calculations, we saw it was 4.522. So we put in that, we apply, close, just making sure everything else is working. We have our interior surface body, our outlet, pressure outlet on the side here, and then our walls, which would be first the walls of the wind tunnel and the flat plate itself. So next, as we're going to need the drag forces, we need to make sure that our methods, so making sure everything here is the same. We have this on simple, nothing too fancy. And then controls, everything here should be fine. And then report definitions. Oh, we need to both measure the drag force and the lift force for our calculations here. So you would go to report definitions, and then this is already in here, but you can click new, and then what kind of report do we want? Force report drag or force report lift. So you would pull that up, pulling up the drag. Here's what would appear. So making sure drag is along our X line, the drag is horizontal, and then comes out to drag file, drag plot. And then here, ANSYS is a little finicky when it comes to finding the drag coefficient directly. So in this case, we're just finding the drag force. And since it's going to be along the plate, we would just select all the zones of being the plate. Now, I had it again individually so that because I wanted to see what the force was along each part of the plate. But for the purposes of our CD calculations, we're going to use the net force. And then we would do the same thing for lift. Lift force, all the plates, lift file, lift plot, and this time along the y-axis as lift is vertical. Okay. All right, so we're done with report definitions. Monitors, this is where the files would be, the plots would be, should we need that. That just leaves with initialization. Double click on that. So hybrid initialization, actually making sure everything else is needed. We're done with that, done with that, done with that. Actually done with boundary conditions. Reference values. So for the rest of our calculations, density 1.225, temperature, okay. Viscosity, we're going to need that for a Reynolds number later, as well as the density. So we will go to initialization, double click, initialize, Then hybrid initialization is done. So then we go to run calculations. How many iterations? 150. That seems like a good convergence point. And you could calculate. And now it begins. Now this is going to take longer than it did in the previous lab, as this time we're trying to do so much more at once. So as you can see here, it's going to do 1, 2 iterations. Here, it's doing the residuals for the lift. If I click here, you can see it's starting to do the residuals for the drag. And then here would be the residuals for x velocity, y velocity, energy, k epsilon, things like that. So you can see it is very, very slow. It'll take a good while before it finishes calculations. So I'm going to come back when it's all done and continue from there. All right, after a couple of minutes later, calculations are now complete. So let me have the recording, click OK. And then here we are, we got our mesh right now. So everything should be printed out here. So now to get our required plots, we go to graphics, contours. They're already here, but if you need to do it yourself, you just double click on contours. You have your name. You can click the contours you want. So I did all the different types of pressures. So you can do pressure with static pressure, dynamic pressure, total pressure, what you need, right? If you want to do velocity, velocity, magnitude, you would click all the surfaces, compute, save and display. So to show here, I double click the velocity. As you can see, velocity, magnitude, interior surface body. So compute, it shows the values, click save and display. And right here, it's the graph. As you can see, velocity is weakest at the entrance of the wind tunnel, speeds up as it progresses through, and then once we get the test section, makes a little bit, but zooming in. Once we get to the test section, you can see it spikes, and then once it impacts the blockage, that's when it accelerates around, specifically here on the top corner as it started rotating up. So naturally, it's going to speed up faster here, and then just behind the blockage is when it slows down again, and you can see the wake of the wind behind it. And I did the same thing with total pressure, just save and display. You can see how that's there. Very cool. And do the same with dynamic pressure. There. And then static pressure, which we put in the report. All right. Now to get the velocity vectors, pretty easy. You just pull up vectors, the velocity vectors right there. So then the surfaces that we're going to see it coming from are the inlet and inlet interior surface body. I set the scale to 1 skip 0, as this shows lots of the arrows, and then made sure to draw a mesh for the flat plate and the walls. So you click display so you can see it there, and close, and then again once more compute, save and display. And here we'll start pulling it up. This one might take a little while too because all the arrows that are being formed to show the vectors. Make sure not to click anything around here or it can delay loading the image. Click close. As you can see, it looks very similar to the velocity contours, but once it's here, you can start zooming in around the blockage. And we're a little laggy, but you can see how the flow of air through the tunnel passes around the blockage. See, it's already sped up until impact, and then here it extremely speeds up and then slows down behind in the wake. Okay. Now, if you would like, you could also do the same thing with path lines. So, double click path line. I dubbed this a streamline. Selected all the surfaces, except for walls, particles, particle ID, save and display. Again, this is just a different way of seeing flow in the wind tunnel itself. Yeah, calculations complete. Should show it in a little bit. Again, it takes its time. I had a step size of 0.01, tolerance 0.001. Oh, there we go. It's starting to load. You can see it's considering. It's flying up. All right. Close here, and you can see that's where the blockage was. And then we zoom out some. It's a very cool looking way just to, again, just another way that you can see the flow passing around the blockage in the tunnel. All right, so for our lift and drag coefficients, now that we've run the reports, so if we go back to report definitions and we click drag, for instance, everything's already here. We can click compute and OK, and here it'll print out the drag forces surrounding the plate and then the net drag on the plate. And we can do the same thing for lift and making sure it's all the same. We click compute, and here's the lift force surrounding the plate and then the net lift. So to find the coefficients, we would have to use the formula for coefficient of drag / coefficient of lift, which is the force divided by 1/2 rho u squared times a, with u being our velocity in the test section. And since this is a 2D flow, instead of an area, it is just the length being affected by said force. So in this case, for the horizontal flat plate, is just how long it was diagonally, which in this case I had it at 0.027, as explained before. It just angled the plate and reduced the dimensions based off of that angle. So doing the calculations, as you saw, we had drag force at 0.72. So putting that in for coefficient of drag, we got about 0.19, and a Reynolds number, which is rho u v over, rho u length divided by viscosity, which, as we saw, density rho was 1.225, viscosity about 1.79 times 10 to the negative fifth. And it was a feed test section. Here about a lift of, a row of 2.7 times 10 to the 4, which if we reference back to the chart, let's see, at a horizontal flat plate at about 10 to the 4th, we should have somewhere in the bigger than 0.01, less than 0.1, let's say about 0.6 for horizontal flat plate. And as it becomes more and more vertical, for said Reynolds number, it should be increasing more drastically. So if I go back here, say on a horizontal flat plate, our drag was 0.2, which at 60 hertz. Makes sense? Sorry, at drag was 0.2, the coefficient was 0.058, which makes sense. But as we angled it up, our coefficient is now 0.191, which is much higher than 0.058. So look here. And 191 would put us about here, while our horizontal flat plate was about here. Okay. For a comparable Reynolds number. Yeah. And the last thing that we need to do was for the streamlines. So we can close this. So it saves the file every time we close. Now I can go to results. I'm going to edit. Now from here we can pull up the velocity streamlines in the CFD post. I don't know why it's asking that. I've pulled this up multiple times. There we go. It's loading in. Give it some time. Okay. Here is our wind tunnel. It's time to come in. There we go. So as you can see, it already has a streamline, but to show where I got it, you just go up here to where it says streamline. I'm just going to call the streamline one for now. So then it'll pop up asking what type. We want a 3D streamline for all domains, starting from symmetry 1. So that tells it it's going to go horizontally here. All of them equally spaced. And I used 100 points of reference. So then we'll click apply. And exactly as it appears on the 10, there's the streamline. So as you can see, it looks very similar to our velocity contours. If I zoom it out enough, very, very similar. Zooming back in. and just shows the flow of air upon impact and going around the blockage. And that is how you do everything for the 60 hertz, 10-degree angle of attack flat plate for Lab3. So I hope this is a good tutorial. Have a good rest of your day.